There's a place in the universe where physics breaks down, a region so extreme, not even light can escape it. Most people think of black holes as simple cosmic vacuum cleaners, bottomless pits that suck in matter and vanish it forever. But the more we've learned, the clearer it's become that this couldn't be further from the truth. Because the space around a black hole isn't empty, it's not quiet, and it certainly isn't simple. In fact, black holes are surrounded by some of the most violent, energetic, and downright bizarre environments in the entire universe. From matter that glows hotter than any star, to paradoxes that challenge the very nature of reality, black holes are not just endpoints. They're engines. They're laboratories. They are riddles wrapped in enigmas. And the more we look, the weirder they get. At first glance, they appear straightforward. A dead star, crushed under its own weight, collapses so completely that it forms a singularity, a point of infinite density where space and time themselves cease to make sense. Surrounding that is the event horizon, the point of no return. Once crossed, not even light can find a way back. It sounds final, but that's just the beginning of the story. The area outside the event horizon, the so-called black hole environment, is where things get wild. Imagine matter spiraling inward, not falling straight in like water down a drain, but caught in a whirlwind of gravitational torment. These swirling bands of gas and dust form what we call an accretion disk. But calling it a disk might be misleading. It is a cosmic forge, where matter crashes into matter at speeds approaching light, heating up to temperatures that dwarf those inside stars. In these zones, atoms are ripped apart into plasma, and friction lights up the darkness with a brilliance so intense it can outshine entire galaxies. This is why we can see black holes at all, not because we see them directly, but because of the chaos they cause around them. Some black holes have jets of energy blasting out of their poles, stretching for millions of light years, like cosmic lighthouses that can be seen across the universe. But even these beams of radiation aren't fully understood. How do particles trapped in gravity so strong suddenly get ejected at nearly the speed of light? And how can something that pulls everything in produce jets that push matter out? And then there's time. Time behaves differently near a black hole. To a distant observer, something falling into one appears to slow down, frozen forever, just before crossing the event horizon. But for the object itself, the plunge happens in seconds. It's not just space that's curved here. Time itself bends, it stretches, it fractures. This bending is so extreme that it separates observers, creating different realities depending on your point of view. And, that brings us to something even more bizarre. Stephen Hawking once suggested that black holes don't last forever, they leak. Through a process now known as Hawking radiation, quantum theory predicts that black holes slowly evaporate. This idea hinges on the strange behavior of empty space. Even in a vacuum, quantum fields fluctuate. Virtual particles blink into existence, always in pairs. One particle and one antiparticle. Usually, they annihilate each other in a flash. But at the edge of a black hole, this dance gets interrupted. One particle gets trapped, the other escapes. And with it, a tiny bit of the black hole's mass disappears. Over time, this trickle of radiation adds up. If Hawking is right, every black hole is slowly dying, not in a violent collapse, but in a whisper, evaporating into nothingness. That alone would be mind-bending, but it also introduces a paradox. If matter falls into a black hole and the black hole vanishes, where did the information about that matter go? Quantum mechanics insists that information can't be destroyed, but general relativity seems to say it is. This is known as the black hole information paradox. It's not just a math problem, it's a clash between the two most successful theories in physics. And honestly, no one has resolved it yet. There's another mystery. Black holes spin, and when they spin, they don't just twist themselves, they drag space along with them. This phenomenon, called frame dragging, means that near a rotating black hole, space itself spirals. Nothing can remain still. This effect gives rise to the ergosphere, a region outside the event horizon where all objects must rotate with the black hole. It's here that we discover a strange loophole in physics. Roger Penrose proposed that if you drop something into the ergosphere just right, you can actually extract energy from the black hole. It sounds impossible, but it isn't. The object splits in two. One part falls in, the other escapes, with more energy than it started with. This Penrose process may one day power future technologies, or at the very least, it reveals how much raw energy is hidden in the warped fabric of space-time. Even more intriguing is the photon sphere, a shell of space where light itself can orbit the black hole, not fall in, not escape, orbit in a perfect circle. It's a place where light is trapped in eternal limbo, never quite falling, never quite leaving. Imagine standing in this zone, watching your own image wrap all the way around the black hole and come back to you. It's not science fiction, it's just a consequence of extreme gravity. And if all of this weren't strange enough, consider this. Black holes might not be what they seem at all. According to some interpretations, they might just be shadows, projections of something deeper. One theory, known as the holographic principle, suggests that all the information contained in a black hole might be encoded not inside it, but on its surface. Just like a hologram, where a two-dimensional surface can produce a three-dimensional image. If that's true, then our entire universe could be a kind of hologram. Stars with the true reality encoded on some distant cosmic boundary. It's speculative, yes, but it's a serious idea being explored by serious physicists. And we're only scratching the surface. Some black holes may connect to others through theoretical shortcuts called wormholes. These hypothetical bridges could, in principle, allow for faster than light travel, or even time travel, though no evidence has been found yet. Still, the math works. And in physics, working math is often a precursor to discovery. All of this paints a very different picture of black holes than the one we started with. They're not just gravitational sinks, they're engines of transformation, laboratories for extreme physics, places where our understanding of space, time, energy, and matter is tested and often found lacking. They defy our intuitions, they contradict our expectations, and they demand new theories. And what's perhaps most surprising is how accessible black holes are becoming. Just a few decades ago, we weren't even sure they existed. Now, we've photographed one, we've mapped their mergers using gravitational waves, we've tracked stars orbiting invisible points in space. And with every new observation, the mystery deepens, because as our tools get sharper, the simplicity of black holes falls apart. The closer we look, the more complex and beautiful they become. Maybe, in the end, black holes aren't just the garbage disposals of the cosmos. Maybe they're the keys to understanding entropy, to unifying physics, to revealing what lies beyond the known universe. They challenge us not to look away, but to look deeper, because in the heart of darkness, there is light. And as we continue this journey, as telescopes peer farther and theories grow bolder, we might come to realize something profound. Black holes aren't the end, they're a new beginning, a place where everything we thought we knew gets rewritten, and if that's not complicated, then nothing is.